My name is Robert Keelan. Today I'm going to be talking about structured logging for autonomous vehicles, and I'm the Code Health Team Lead at Argo AI. So first we're going to be going through some of the high-level requirements about debug logging systems for autonomous vehicles. I'll give a high-level picture of what I consider like my ideal debug logger to be. Then we'll talk about its implementation in C++17, and then go through what some of the improvements are to that implementation in C++20. And then finally, I'll talk through some integration with an error handling framework afterwards. So debug log is a record of events that occur during the execution of a program, and they typically have the contents like what you see on the right. File name, function name, line number, a semantic logging level, something like error, warn, or info, a timestamp, and then the actual payload that the developer wanted to include in the debug log. And for autonomous vehicles, there are a lot of different users of debug logs. So the first person that will actually look at a debug log on an autonomous vehicle is typically a co-pilot. So they're sitting in the front seat with a laptop open. They'll have a visualization about what the car sees, and they'll also have a terminal or some kind of view into what the debug log is showing. And they're responsible for doing kind of a rough classification of any errors that occur during the execution or while the vehicle is running. Then you'll have a triage engineer. So once that log or all the data from the vehicle has been uploaded to the cloud, you'll get a triage engineer that'll look through that same debug log and do a finer grained classification. And then finally, you'll have a developer, once they need to fix a bug, they'll use the debug log as an important tool in order to help narrow down what's going on. And as you kind of get from vehicle operator to developer, you get people that are more specific or more in tune with what's going on with the internals of the program. So it's important to give people like vehicle operators and triage engineers the most context possible in order to help them do a rough classification of these errors. And then finally, you might want to have developers write cloud tooling against a debug log. So find out how many times a certain debug log message was hit, or try to find correlations between certain log messages. So there are two basic debug logging paradigms. There's text-based logging, which basically outputs human readable strings. And then there's structured logs, which outputs the data in some kind of machine-friendly format. So that could be something like JSON format, what I'm showing on the right, but it could be an equivalent binary format. So they both have their pluses and minuses. Text-based logs are great for humans to look at. Typically, they output actual human, like sentences or human readable strings for the actual payload. So if I'm looking through a whole wall of text of these debug log statements, it's actually really easy for me to pick out which ones I need to pay attention to. It's easy for your eye to pick out info. Oh, here's my error. Maybe that has something to do with the current issue that I'm seeing. And then for structured logs, you could even take this a step further. So not only could you structure, let's say, all of that metadata, the file name, function name, but you could also structure the payload. So this is what that equivalent payload would look like in some kind of structured format. So it'd be very easy to write a tool against this debug log statement and pull out index and size and see every time this debug log statement was hit, what kind of indexes and sizes was I actually seeing. Okay, so ideally, I'd have for an autonomous vehicle, I'd want to have something like the interface that we see above, where I have a log error macro, and I'll talk about why macros may be important here, and this is maybe one of the cases where you actually want one. But basically, the interface that we have is an FMT or stood format compatible format string, mostly, and I'll explain why I say mostly. And then you have your dynamic replacement fields, IDX and SIZ in this case, and those are the actual values you want to stick in the double curly braces in that format string. And I say mostly compatible is because we want a clean interface for actually naming these replacement fields. So if I write a tool, I'd want to actually write a tool that says, okay, give me all of the size elements here. I don't want to have to pull it out with a regex or something. I want to actually name it. So before we actually use that format string with stood format or FMT, we're going to strip out those size names. So those are still positional fields. They're just a clean way of getting that structure that I talked about on the right with index and size. Okay. And this is, like I was saying before, this debug logging is one of the cases where you actually might want to have a macro. And I actually think it's pretty important, especially if you're trying to optimize your code. So for example, if IDX or SIZ wasn't a variable like it is here, but a big complicated expression, that's going to produce some output. And I wanted to optimize that code out for a certain debug logging level. Using a macro is an easy way of doing that. So in general, right, you should follow the same rules that you do with assert with debug logs and not have any expression that produces any side effects. But if the compiler can't tell that, can't look through and actually see that, and can't throw that compute away, then you might end up with code even though you're just not even logging that log statement. So one important optimization that I wanted to talk through about debug logs is the idea of metadata and instance data. So here's the same debug log statement, tried to access index on vector of size. This is what it would look like if I logged it over and over and over again. And what you might notice is that most of the data here, or a lot of the data here, is shared between each instance of this debug log message. So the only things that are actually that actually change every time you log it are things like the timestamp and the replacement fields, index and size. Everything else is shared. So I'm going to call all of the things in blue instance data, the things that can change, and all of the things in green metadata, or the things that are shared between each instance of a debug log message. So in an ideal world, right, my ideal AV debug log system would be able to separate out this instance data and this metadata and log the metadata only one time for a given version of the software. So that way, across an entire fleet of vehicles, I only have to basically generate that metadata a single time. Then all of the vehicles can use that in order to basically unpack that instance data and transform it into something like a human readable string. So that instance data, again, would have the timestamp, the dynamic data, and then some unique identifier that basically tells it which piece of metadata to use to unpack that statement. So this is kind of a high-level picture of how I see that system working, right? In the trunk of all of our vehicles, we have our main AV compute. Sitting up in the passenger seat, you have the vehicle laptop. What should be already on that laptop before the vehicle starts up is all of that metadata, like basically a metadata file that contains all of the metadata. While the AV compute, while we're actually running our program, we send instance data to that vehicle laptop, and using that instance data and the metadata, we're able to generate human readable strings on the fly for the vehicle operators. Then when we load that data into the cloud, we have a single metadata file. Then all the vehicle logs collected from all the cars running that version of the software can then reference that single piece of metadata. So let's talk through how we would actually generate this metadata from all the individual log statements in our program. So the approach that we chose was to basically create a static linked list of all of the metadata when the program starts up. So before main hits, we're going to generate this linked list of all the metadata in our program for each debug log statement so that we can collect it later. So each node in this linked list is going to contain a unique ID, a pointer to some constexpr, to some static constexpr metadata, and then a pointer to the next node. And note that this work is happening when the vehicle starts up, or when the program starts up, but it's a very cheap operation. All we're doing is assigning IDs and doing some pointer manipulation. No actual allocation is happening, all the nodes are static. Okay. So before I go into the actual implementation of our debug log macro, I wanted to talk through these two structs. What I'll call log macro data. So this is the actual data that our log macro is going to generate. It's going to have string views for the file, function name, the format string, line number, and semantic logging level. And then this log statement metadata. And this is the full metadata that we're going to keep, that we're going to store or point to in our linked list. And it basically has all of the same information that log macro data does, plus some additional information, what I'll call type descriptors. And that's basically a way of encoding what types we're sticking in our format string. And I'll explain why that's important later. So this is the implementation of our log error macro. So let's say we have a function foo on the bottom with this log error statement, tried to access index on vector of size. Basically, this whole log error macro is setting up this single call to this log function. Okay, and basically the requirement of that log function is that it's going to take in as arguments all of the var args for that macro, so idx and size in this case. And then it's also, as an explicit template parameter, it needs to take in some kind of object that can generate log macro metadata, basically generate a constexpr version of that log macro data from within that log function. So it's not enough that we can generate a constexpr version of that log macro data outside the function. We need that constexpr version inside. So in order to get that constexpr macro data inside the log function, we create this anonymous struct here. And that anonymous struct is constexpr default constructible, right? And it has a constexpr callable operator that will generate that log macro data. So then from within inside our log function, we can default construct that type that's in the explicit template parameter, and then call its callable operator, and then get a constexpr version of that log macro data. Okay, so kind of the two tricky bits of this log error function are one, that you need to call this __ function outside of your callable operator, unlike file and line, or else you're gonna get the callable operator to be every function in your debug log. And then finally, because we're introducing all these names into our client scope, we need to wrap this whole thing in a do while loop. And you set do while to false, you wrap it in a scope so those names don't leak out. So for example, if you have multiple debug log statements in the same function, you don't want those names colliding. And do while loop is kind of the accepted best practice of doing that. For example, if you had something like an if and then a log statement and no braces, you're probably going to get some unexpected scoping. So the do while loop helps avoid those problems.
You don't want the semicolon if the while false?
Say that again?
You don't want the semicolon after the while false?
Oh, sorry, slideware. Okay, so what gets better about this debug log macro in C++20? Well, the biggest thing that I would like to eliminate is the need for this do while loop and basically introducing names into my client scope. So what we can do in C++20, we get improved support for non-type template parameters. So now we can put, you can imagine putting that __ function macro inside of a template parameter. And now our log function can take something like a fixed string, right? And if you wanted to look at the implementation of this fixed string, this is on CppRef. And basically, it has a deduction guide that will take a C array, figure out what size to make that fixed string, and it will actually store the value of that data in the fixed string. So once you have that value as a template parameter, it's very easy to make a constexpr version of that from within inside that log function. Okay, so now let's talk through the actual implementation of the linked list. We have our log data node. We'll first look at the constructor. We take a pointer to that constexpr log metadata, and we'll store it. Then we want to generate a unique ID. So we just call a genID function, has a static variable counter. We bump the counter every time we call the function and return the value. Then we also have a function, log data head. Again, that has a static variable, and we're going to return a reference to that log data head to that pointer, that log data node pointer, right? And this is going to be the head of our linked list. Then we'll just do an exchange, which sets ourselves as the head of the linked list and sets our next to the previous head of that list. So every time this log data node gets constructed, it's going to get a unique ID and basically add itself to the static linked list. So now let's look at the internals of our actual log function. So first we construct one of those metadata nodes, and that metadata node variable is a variable at namespace scope, right? So this variable is going to get constructed when the program starts up. So that's how we guarantee we're basically generating that static linked list on program startup before main hits. Then we assign a pointer, that's that log statement metadata pointer, and I'll talk through the implementation of that get metadata pointer function next. So if we jump back down to the internals of the log function, all we're doing is doing basically a binary serialization of the ID of that node plus all of the replacement fields. So in the example before, SIZ and index. So now you can imagine in our binary serialized debug log, we're trying to read through and then basically convert that binary representation to a human readable string. So we start reading through, we encounter an integer, which basically is the metadata ID, but now we need a way of figuring out how to unpack the next series of bytes and convert those into a human readable string. And that's what we use these type descriptors for. So basically a type descriptor is just a variant of types where each type basically encodes how to take a class of types or a class of values and basically encodes how they're encoded in binary and how to take those binary bytes and actually convert them into a human readable string. So they could be something simple like these tag types int and float. So that way, if I'm reading my binary data, I know that the next 4 bytes are encoded, let's say, as an integer, and I should display them as an integer. But they could also be more complicated, and we could extend this kind of idea. So for example, we could have an enum type that we stick in our variant. That enum type would basically be a span of pairs of integer and string views. So now, if I log this enum as one of the type descriptors in my metadata, I know I should interpret the next 4 bytes as an integer and then use this lookup table to convert that integer to a human readable string. So this is kind of the key idea of how we're able to encode more complicated types besides the fundamental types in our debug log metadata. It also makes this framework very extensible. And then when I talk about type descriptors plural, really they're just a span or a contiguous view of elements of those type descriptor variants. So now we need to talk through how do we go from types like integer into type descriptors. And we do this using this type descriptor trait. And here's what that trait would look like for something like an integer. So it's specialized for the type int. It's got a static constexpr type descriptor variable, and we initialize that with that integer tag. So now we'll jump into the actual implementation of our get metadata pointer function. The first thing we do is we create a static constexpr std array of type descriptors, and we use that get type descriptor trait for all of our incoming args, unpack it, and now we have a static constexpr std array of all of those type descriptors. Now the log statement metadata, all of those are the same type throughout the entire program. That makes things like serialization, for example, and deserialization of those types much easier. So it's nice to have all of those things be the same type. But the std array has a size parameter, right, in one of its template parameters. So we need to erase that size. So we wrap that std array in a span, right? And this is capital S span because they're not implemented yet in C++17. So this is our own internal implementation. So in order to erase the size of that std array, we wrap it in a span and stick it in the log statement metadata. And then again, we generate all of that macro data that we saw before by default constructing that type F and then calling its callable operator. And then we return the pointer to that static constexpr metadata. So what gets better in 20? Well, in C++20, std vector gets constexprified, right? So we no longer need to do this weird song and dance of having the storage of our data in a std array and then wrapping it in a std span just to get all of that, just to get a constexpr view of those contiguous bytes to be the same types. We could just dump all of the elements in a std vector and be done with that. Okay, so the last thing I wanted to talk through is actually transporting log statements via an explanation. So integration into an error handling framework. So you can imagine you could have this explanation type that has a pointer to your log data node, right? And it also has some kind of container. So it could be a std array, it could be a std vector. But when you know all of your replacement fields are a fixed size, it's nice to have it as a std array. And basically that std array is a std array of bytes, and that's where you would dump your binary serialized replacement fields. Right. So let's say I have a function baz that calls a function foo. That function foo will return an expected type, either a value that I expect in int32, or one of these explanation types about basically with a debug log statement that explains why that function failed. And what's really powerful about this is that I can now stick one of these explanation types in my debug log. Now, in order to do that, you need to add a type descriptor, an explanation type descriptor type to your variant. But once you do that, you get something really powerful, right? So your client now has control of when that debug log statement actually gets logged, right? You decouple that low-level library foo from your actual logging framework, and you allow the client of foo to actually do the debug logging. So for instance, your client can do things like debouncing and only choose to log every, let's say, 10th error message if they wanted to. But also, you could actually start generating, let's say, a chain of debug log statements. So you could imagine creating an explanation type in a low-level library, then it gets wrapped in another explanation type in the next function, and then finally gets dumped into this log error statement. And then what you end up with is kind of a stack trace of all of these explanations as they're getting brought up the stack. So that actually gives you a very powerful way of generating traces and putting them into your debug log. So in conclusion, I talked through a debug logger that produces both structured, basically produces structured output and is able to convert that structured output on the fly to human readable text by combining metadata and instance data. Then I implemented key features of this framework in C++ 17 and showed what we can actually improve in C++ 20. Finally, I created a type that efficiently encodes these debug log statements so they could pass through interface boundaries. One thing I wanted to mention really quickly, I tried, so for those of you who might want to ask, stood source location, I tried to use that for an improvement in C++ 20, but actually couldn't get it to actually fit in the debug, actually create a constexpr version and get the function name to show up correctly. So if anyone has any clues on how to do that, I'd like to hear that after the talk. But that's been minimal structured logging for autonomous vehicles, and thank you.
So you fill out all the metadata stuff pre-main. Does this mean nobody can log pre-main, and how do you keep that requirement?
Yeah. So yes, that is what. Yes. So that is a requirement of the debug logger. You don't actually get a debug log before main hits. Now, actually, it depends. It depends on how you want to do the logging, right? So that debug log statement always has access to that metadata. It's only if you wanted to. You don't get that property of just being able to write that unique ID. And then dumping out the dynamic serialization data. If you wanted to log before main, you would need to log all of the data because that unique ID hasn't been assigned yet. So that's really the only requirement, is that before main hits, you can't use that compressed format.
Did you experiment with lazy generation of metadata ID or anything like that?
Yeah. So that was actually originally how the library was implemented. But for autonomous vehicles, that's kind of a scary property to have. So you can imagine if I'm in a fault condition, lots of people are going to be logging data because they want to know, having debug log statements because they want to know what's going on. And while we're in a fault condition and we're already spamming the debug log, we'd be writing the metadata because we'd be hitting those instances of that metadata for the first time.
Thanks.
Yeah.
A couple of questions. First,
Sure.
I didn't see anything regarding threading. Do you have a single thread that actually writes the log? And secondly, regarding the log, I may have missed it at the beginning if you had it.
Yeah.
And then furthermore, writing the log, you constantly writing, or do you keep it in memory and then dump it one time?
Sure. So I didn't talk through threading. Basically, all we're logging is binary serialized data. That's kind of a separate system for us that we already need to optimize. So once we generate that metadata, once we get the unique ID and get our dynamic replacement fields, we're just going to log them in some binary format. And you could do that using any of the. There's a lot of serialization frameworks out there now. Ours basically, for each client thread that we want to log on, we have some kind of ring buffer. Then we have a background thread that services each one of those ring buffers and then outputs the data to the serialized output. Prior to this, our previous debug logging system basically took each debug log that you wanted to write and put it in its own message, basically something like a protobuf or equivalent. But now, because the messages got so small, after removing all of that metadata, we actually are able to batch them up now and send them out in small batches of these debug log statements. Yeah.
So one little question: have you experienced some compile time performance penalty for creating structs on every log line and so on? I mean, some other
Sure.
systems do a pre-processing of the files and generate the metadata offline as a generation step.
Sure.
So what's your experience with that?
Yeah, so we recently ported our code base over to this and didn't notice any significant decrease or increase in compile time. And you can think about, we generate structs, anonymous structs, or the equivalent all over the place in our code already, right? We use lambdas everywhere. Those are technically their own type. They need to be remembered by the compiler. So this isn't really anything new. We're not generating that many types.
So I was just curious if you have a way of aggregating these logs across multiple processes. Like if you have multiple processes that are communicating with each other, do you have a way of kind of synchronizing and aggregating these type of logs together?
So let's see. So the way our system on vehicle actually works is we have a debug log channel, and each time a process writes that debug logging channel, you'll basically get some kind of ID for that process. So then when we actually go to decode it, in the actual, we have a little program that all it does is basically unpacks that instance data. We basically do a lookup based on that process ID. Okay, what piece of metadata do we need to look up, and use that metadata file to unpack that instance of the debug log.
Thanks.
Yeah.
Hey, I may have missed this, but is it the macro expansion that causes the struct to be declared so that you can gather all of the static log messages before main runs? How is that?
Sure.
How is that gathered up? And is it a global?
Yes. So let me jump back to that. Yeah. Okay. So we create a type. That type can be constexpr default constructed and has a constexpr callable operator. That way, when we get into and we pass that as an explicit template parameter f in our log function, right? So now we have this metadata node. That metadata node is a variable at namespace scope. So when we write out this function, that metadata node is going to be instantiated before main.
So
right?
it's instantiated
Statically.
at global time.
Excuse me?
It's instantiated at global time or static construction
Correct.
time before main.
Correct.
And that would imply that the order is not specified between compilation units
Correct.
for the instantiation.
Well, yeah, it's going to be consistent, right? Once you compile your program, it's going to be consistent.
Right.
But once I make a change to that program, I need to regenerate that metadata file.
Okay.
Yeah.
Hi, thank you for your nice talk. Do you have any plans of open sourcing any of this, or?
Yeah, so that's part of the reason why I wanted to present at this conference and wanted to kind of gauge some interest in open sourcing this library. It would be the first library that Argo would open source, so there's some trickiness with that, and I don't quite know what I'm getting into. Yeah.
You provided a lot of code already, so.
Right. So yeah, so that's part of the reason why I wanted to present here, to see how interested people would be in this library, and we can work on cleaning it up and potentially open sourcing.
Okay, thanks.
Yeah, no problem.
Hi. We also have a very similar product, and we are on our way to open source that. Maybe we can collaborate on that.
Yeah, that'd be great.